Hey everyone, welcome. Today we're working on the 1D dynamic programming questions from the LeetCode roadmap. So dynamic programming questions, or DP, are often combinatorial questions or optimization questions. And these questions often give us a goal, for example, looking for the maximum value, looking for the minimum value, or looking for how many ways there are to do something. So to solve these questions and reach our final goal, we often have to split the questions into a bunch of smaller steps. Oftentimes we call them subproblems. So we need to evaluate these subproblems all correctly and put the results of the problems finally into our goal. So that's an overarching idea of dynamic programming. It takes a big problem, breaks them down into smaller subproblems that are easier to achieve, and these subproblems build upon each other to finally reach our final goal. So let's take a look at the very first question here, climbing stairs. So in this question, we're climbing a staircase. It takes n steps to reach the top, and each time we can only climb either 1 or 2 steps. So how many distinct ways are there for us to climb to the top? So in this question, n is 2. Remember, we start on step 0, so we need to climb up 2 stairs to get to the top. So there's 2 different ways to climb 2 steps. We can first climb 1 step, then climb the second step, or climb 2 steps in one go. So the answer is 2 here when n is 2. So in example 3, there's 3 different ways to climb to the top because we can split it into 1 step and 2 step, or 1 step first, then 2 steps, or 2 steps first, then 1 step. So each of these are unique ways, so the answer here is 3. So this is a dynamic programming question because we can split climbing stairs into different subproblems. So we're going to split it to subproblems based on the number of stairs we've already climbed. So for example, looking at example 2 here, if we've already climbed 2 stairs, there's 2 different ways to climb 2 stairs, as we see from example 1. There's one way where we climb 1 step and then 1 step, or another way where we climb 2 steps altogether. So we have the answer from example 1, so the answer is 2, with cases 1 and 3. So however, there's also case 2 where we climb 1 step first, then 2 steps. So that's the case where n equals 1. n equals 1, the output is also 1 because there's only one way to climb 1 step. So we add the output of n equals 2 and n equals 1 to get our output for n equals 3. So this is the main idea behind this problem. At every step, at every index I, we can take a look at how many ways there are to get 1 step down and how many ways there are to get 2 steps down, because we need to either climb up 1 stairs or 2 stairs to reach every index I. So let's create our DP approach. Let's create an array. We call this DP, and it's going to be an array of zeros, and the length of this is n plus 1 because we first start at index 0 all the way to index n. So there's n different elements in this array. So at the start, DP of 0, this is going to be 1 because there's one way for us to start at step 0. This is where we start. And DP1 equals to 1 as well. So we're going to set this manually. DP1 equals 1 because there's only one way to arrive at stair 1. And it's that we take a single step, like here. So next we do a for loop to look at all the other cases. So we've already covered cases 0 and 1, so we can do for I in range starting from 2 all the way to n plus 1. So this goes all the way to n, this is non-inclusive. So dp of I, we said that it depends on how many ways there are to reach 1 stair down and how many ways there are to reach 2 stairs down. So 1 stair down, we can say 1 stair down. This is dp I minus 1 because we've already calculated I minus 1 since I minus 1 comes first in this for loop. We've also already calculated I minus 2. So 2 stairs down, this is equal to dp I minus 2. We've also already calculated that. So to calculate dpi, there's only 2 ways to reach I, either from 1 stairs down or from 2 stairs down. So all we're going to do is add these up. So 1 stair down plus 2 stairs down. So that's what make up dp at I. So after that, we're going to do this all the way until n minus 1, or all the way until n. So we're going to return dp at n. This is how many ways there are to climb n steps. However, there's one thing here where we set dpi equals to 1, dp1 equals to 1, but it's possible that n is already equal to 1. So in which case, this is going to be array out of bounds. So we don't want to do that. So we do a special edge case here. If n equals to 1, we just return 1. So this is a special edge case just so we don't get array out of bounds. Let's try running that. Cool. So let's emit it. Nice. So moving on to the next question, minimum cost climbing stairs. So in this question, we're given an integer array cost, where cost at I is the cost of the ith step on a staircase. So once we pay the cost, you can either climb 1 or 2 steps. So this is very similar to the previous question, except there's a cost for standing on a step. We can either start from the step with index 0 or the step with index 1. So let's look at an example here. We can either start here or start here. These are the two options. So we choose to stand on the step at index 1, so the 15 here, and then we take 2 steps. So our goal is going to be here, 1 off the end of the array. So we take 2 steps, go to the 20, and then go to our goal. So in which case we only pay 15 because the cost is the cost of leaving this stair essentially. So there's another case where we can just keep hopping between ones. So we only pay 1 at a time. We step on 6 ones, so we're going to pay a total of 6. So this is super similar to the previous question because we're only moving up either 1 step or 2 steps at a time. So we can just look at the cost of going 1 step down or 2 steps down. So let's set n equals to the length of cost. This is how many steps we need to go up. And just like before, dp equals to 0 times n plus 1. Except this time, dp is no longer storing the number of ways, so it's not a combinatorial question anymore. It's now an optimization question. So dp is storing the minimum cost at every index. So now for I in range, starting from 2 all the way to n plus 1, we can do this because cost has a minimum length of 2, so we don't have to worry about out of bounds. And at the start, dp at 0 and at index 1, both of those have cost 0 because we can start from any of those. So again, we have 1 step or 2 steps. 1 step. If we do 1 step, that is, we're paying the price of leaving that stair. So the price of leaving that stair is going to be cost at I minus 1, so that's 1 step, plus how much we've already paid to reach that step, which is dp I minus 1. So we could also have gone 2 stairs, so 2 steps. We need to pay the cost of leaving that stair, so cost I minus 2, plus dp I minus 2, which is the cost for us to have reached this 2 step. So after that, we can just calculate dpi. So we want the minimum cost. This question is called minimum cost of climbing stairs. So we're going to take the minimum of 1 step and 2 step, whichever one is cheaper, and we're going to say that's the cost of reaching our current step, or the stair at index I. So 1 step, 2 step, 2 steps. So this is the minimum cost of reaching the stair at index I. We store that in dp, and then we're going to use this for future iterations of our for loop. So finally, we're done all the things up to n, so we can return dpn. This is the cost of reaching stair n. Let's try running that. Cool. So this question, pretty similar to the previous one, except instead of counting how many ways there are to reach different stairs, now we're counting the minimum cost to reach different stairs. So instead of adding the previous combinatorics up, now we're comparing the minimum to reach these stairs plus the cost of departing from that stair to calculate how much it costs, or the minimum of how much it costs to reach our current stair. So that's this question. Moving on to the next one. This question is house robber. So in this question, we're a professional robber planning to rob houses along the street. Each house has a certain amount of money stashed, and the only constraint stopping you from robbing each of them is that adjacent houses have security systems connected, and it will automatically contact the police if 2 adjacent houses were broken into on the same night. So what this is saying is that we can't rob 2 houses which are side by side. So looking at example 1 here, we can't rob the 2 and the 3 because that's going to alert the police. So instead, the best way is either the first one and the last one, the first one and the 3, or the 2 and the 1. So the optimal output, the maximum amount of money we can take, is the 1 and the 3 because they're not side by side, and that gives us 4. So this question gives us an array nums representing the amount of money in each house. We want to return the maximum amount of money we can rob without alerting the police. So basically, we can't rob adjacent houses, but we want the maximum amount of money. So in this question, first let's create n equals to the len of nums. This is how many houses there are on the street. So we're going to also use a DP approach for this question. DP is going to be an array, and DP is going to store how much money we have if we robbed every house, including or prior to this one. So DP is going to be start off as 0, and we're going to set that array to be of length n. So if we only had one house on the street, if we only had the very first one, then the maximum amount of money would be to take from that house. So if we take from that house, we're getting nums 0, or the amount of money stashed at house 0. So however, if we have two different houses, for example, the house at index 0 and the house at index 1, then we have two different options. We can't take both of them because that's going to alert the police because they're adjacent, so we can only take one of them if we only have two houses. So it makes sense that dp1 equals to the maximum of nums at 0 and nums at 1. We can only take one of them, so we're going to take the maximum of those two. So now, as we get more houses, we're going to use a for loop for our DP approach. So for I in range, we did 0 and 1, so we can do 2 all the way until n, all the way until the last house on the street. So at every house, we have two different options. We can either rob the house or we can not rob the house. So how much money do we get if we rob the house? If we rob the house, let's call that rob house. This is going to be nums of I, so we're taking the money from the house, nums at I, plus how much money we could rob from two houses prior. Because if we rob the house at I, for example, if I is here, we take the 3, we can't take the 2. So we take the maximum money starting from 2 indices down. This is 1 index down, this is 2 indices down. So we can also take the maximum amount of money with the 1 or any houses prior. So this is going to be stored in dp I minus 2. Not I minus 1 because I minus 1 is adjacent, so I minus 2. So this is how much money we have if we do choose to rob the house. But we could also not rob this house. So if we don't rob it, not rob house, how much money do we have? We don't get nums of I in this case, but we are allowed to rob the previous house. So how much money can we get in the previous house? We already calculated that with dp I minus 1. So at every house, we are given these two options to rob it or not rob it. We want the maximum amount of money, so we take the maximum of rob house and not rob house. So dp at I equals to the maximum of these two. So after we have this dp, this is going to be evaluated for every I from 2 to n minus 1. So the end of the street is going to be n minus 1 as we go from 0 to n minus 1. So that's going to encompass all the houses, which means we can just return that. So return dp at n minus 1. Let's try running that. Cool, let's submit it. List index out of range. Okay, we're setting dp at 1 when the index is only, or there's only one term, so this is going to be out of bounds. In which case, if n equals to 1, if there's only one element on the street, we're going to return that element. So if there's only one house, we're just going to rob that one and get the value nums at 0. Cool, that worked. So moving on to the next question, house robber 2. So this question is basically the same as the previous one, except this line here. So each house has a certain amount of money stashed, but all houses at this place are arranged in a circle. It's no longer a straight line street. That means the first house is neighbors with the last one. And also we can't rob any adjacent houses. That's going to alert the police, and we want to return, we're given an integer array nums representing the amount of money at each house, and we want to return the maximum we can rob. Okay, so this question is basically the same as the previous question. The only twist to it is that this street is now a circle. So we can't rob both the last house and the first house in one night. So what does that mean? We're either robbing all the houses from this array, 0 and 1, or this array, 1 and 2. So we can rob the houses, every house in the first highlighted section, so excluding the last one, or we can rob every house in the last section, excluding the first one. Because there's never a case where we want to rob both the first house and the last house. So looking at another example here, we can just run our previous robbing algorithm on the first 3 elements to get the maximum if this was the street, or we can run that algorithm on this part if this highlighted section is the street. So we never want to run our algorithm on all 4 elements because it's possible that the algorithm chooses the first house and the last house. It's not the case in this example, but it is possible if the first element and the last element are very large. So knowing that we don't want the first and the last to ever be together, one way is to split this into 2 different sections. So we take the first street, which is from the first element all the way to the second last element, and from the second element to the very last element. So these 2 different new substreets of this new circular street is going to be our streets for our first robbing algorithm to run on. So taking our algorithm, we can just copy this over from the previous question. So let's call that rob1 for house robber 1. This is going to take in nums, and we're going to throw in that algorithm just like we did before. So using this, like I said, we're going to only call it on the first part, so excluding the last house or excluding the first house, because the first house and the last house should never be together since they're neighbors. So we can do, all we have to do is find the maximum of these 2 subarrays passed into rob1. So we are returning max rob1 passed in nums from 0 all the way until the last element, but non-inclusive, and rob1 nums from 1 all the way until the last element. So these 2 different ways encompass all the ways we can rob these 2 houses without the first and the last being neighbors. So there's a special edge case again. If len nums equals to 1, if we only have 1 house, then we're passing in rob1 as an empty array. So we're passing in nums from 0 to 0, but it's non-inclusive, so this is going to be an empty array. We don't want to do that because this is going to give us an out of bounds error since we're setting dp0 to be nums at 0. So we don't want that, so we're going to just return nums at 0 here to avoid this null pointer exception. So let's try running that. Cool, let's submit it. Nice. So this question is pretty similar to the previous question. We're literally reusing the whole algorithm in the previous question, but instead in this case, we have to take a look at what we have and notice that the first house and the last house can never be robbed on the same night. So it's safe for us to split this input into 2 different arrays, one excluding the last element and another excluding the first element. So now we find the maximum with our first algorithm on the first array, here 1, 2, 3, or the second array, here 2, 3, 1. So the maximum of these 2, running both of these previous algorithms and taking the maximum of those 2 is going to give us the maximum in robbing a circular street. So moving on to the next question. So longest palindromic substring. So we're given a string S and we want to return the longest palindromic substring in S. So a palindromic substring is basically a substring, which is a non-empty sequence of characters. So it has to be some characters that are continuous and not empty. And also it has to be palindromic, which means it reads the same forwards and backwards. So in example 1 here, the longest one we can see is either BAB or ABA. They both have length of 3, so we can return either of those. So in example 2, the longest palindromic substring is going to be BB. So palindromes, they always have a central character, and that's how we're going to find all the different palindromes. For example, in palindromes of odd length, the center here is going to be B, If palindromes have even length, there's going to be two of the same character in the middle. For example, here the two center characters are B and B. So we can take a look at every possible center character or two center characters in case they're the same and see if we can find the longest palindrome starting from there. So the center character could be literally any character in the string, so we're going to have to iterate down the string to look at a central character. For example, this B, we need to see if it could form the longest palindromic substring. If not, we're going to move on to the next character as the center character. So if this A here is the center character, then the longest palindromic substring it can form is BAB, because we can't go out of bounds. So BAB, and then we're going to compare that with the previous answer, which is B. B has a length of 1, BAB has a length of 3, so BAB wins, and that's going to be our answer. So we're going to do that for every possible center, which is every possible character in S, and we're going to compare the lengths. So this is a DP question because we're just using S to compare, so the characters in S never change, but we can keep the longest answer and compare our answer with that longest to see if we generated a longer palindromic substring. So first of all, let's create a character n. N is going to be the length of S, so our lives are easier, and our initial answer could just be nothing. So we need to create a function that checks the longest or returns the longest palindromic substring starting from a central character. So let's define check palindrome. So what this check palindrome is going to take is that we're going to try to find the longest palindromic subsequence, and we're going to return that. So let's actually code up how we call this. So for I in range n, remember we're trying to have every letter be the middle here. So longest odd, let's create longest odd. Longest odd is going to be the longest palindromic substring, assuming the length of the palindrome is odd. So the center character is going to be I here, or the character at index I. So we can check palindrome, and the starting character is just going to be I. The other starting character, in the case that it's even, is going to be I as well. When it's even, it's going to be I plus 1. So longest odd is going to be check palindrome I, and longest even is going to be check palindrome I plus 1. So this check palindrome function is going to return the longest possible palindrome starting with the center of a single character or two different characters. So now let's create our check palindrome function. So first we need to generate a longest. This is our return. Initially it's going to be nothing. So first we need to, let's pass in our parameters. Let the left character be L and the right character be R. So first we need to make sure L and R are in bounds, because sometimes we can try reaching out of bounds of S. That's going to create an error. So while L is greater than or equal to 0 and R is less than N, so both L and R are in bounds, and we want the left and the right to be equal or the same, because that's what defines a palindrome. So S of L has to equal to S of R. So as long as these are equal and it's in bounds, the longest is going to equal to S from the character L all the way to the character R. But we want R to be in bounds of the string, so we do R plus 1, since the string slicing is going to take the second parameter non-inclusive. So now we can try L to be further left and R to be further right to see if we can find an even longer one. So L minus equals to 1 and R plus equals to 1. And this should be inside here. So now after that we can just return longest. So longest is the longest longest substring that we found that starts from I or I and I plus 1. So now we need to compare these lengths to the lengths of our answer. If this is longer, then this is going to be our answer. So answer equals to longest odd if the length of longest odd is longer than answer. So len longest odd is greater than len ans, otherwise ans will stay answer. Else, so we have the wrong syntax here. Otherwise, it's just going to stay as answer, and we should also compare with longest even. So ans compare with longest even if len longest even is greater than len ans, otherwise ans is just going to stay as ans. So now we've checked every single possible starting center for all the palindromes, and we could just safely return answer because we always compared it to see if answer could be longer. So now we can just return ans. Let's try running that. Cool. That's accepted. Let's submit it. Nice. So this question is more of a two-pointer idea than a DP question, to be honest, but it's included in the DP questions roadmap. So we're going to do it as a DP question. So like any palindrome question, we need to check for the longest palindrome by stepping one at a time to see if the left is equal to the R and L and R are both inbounds for the string. As long as they are, we can try to look for a larger palindrome given that L and R are still equal. If that's longer, then we could return the longest. So then we compare the longest even and longest odd, which are palindromes of even and odd length starting at every center. If any of these are longer than answer, we're going to set answer to that. So that's it for this question. Let's move on to the next one. Palindromic substrings. So given a string S, what we want to do is return the number of palindromic substrings inside of it. So a string is a palindrome when it reads the same forwards and backwards, and a string is a continuous sequence of characters within the string. Cool. So very similar to the previous question, instead of looking for the longest palindromic substring, we're looking for the number of palindromic substrings. So looking at example 1 here, ABC, remember each character itself is a palindrome because it reads the same forwards and backwards. So we only have 3 different characters, which means we have 3 distinct palindromic substrings, which are A, B, and C. So example 2, we have A. There's 6 different palindromic substrings, so we can take duplicates here in our answer. So each A is its own palindromic substring, so 3 A's, and 2 AA's because we can take the first 2 as a palindromic substring and then the second 2 as a palindromic substring. And a single instance of AAA because the whole 3-letter combination is also a palindrome. So this question is super similar to the previous one. We can create our helper function, but instead of getting the longest in check palindrome, instead we should do count palindromes, which is the number of palindromes we actually encounter, starting from every single center. And just like before, a center could be of length 1 or length 2. So let's do the same setup as before, n equals len s, and answer equals to 0. So initially we have 0 palindromes. So let's define this, let's call it count palindromes. So this is going to take in our centers, L and R. So initialize count, initialize that to 0. So just like before, we need to check L and R inbound. So while L is greater than or equal to 0 and R is less than the length of S, and also S of L equals to S of R. So while these are equal, the count should plus equals to 1 because that means S from L to R is a palindrome. So after that, we should decrease L by 1 and increase R by 1. So basically expanding the length of the palindrome by 1 on each side. So after that, we encounter something that's not a palindrome, or we reach the boundary of the string, so we can return our count. So now we want to have a palindrome start from every single possible center. So for I in range n, every character here is a possible center. So our answer should increase by the amount count palindrome. So assuming we have a even center, so if we have an odd center, that means we start at a single character, for example B, or for example this middle A here. Or alternatively, ans plus equals count palindrome dromes I and I plus 1. So don't worry about this I plus 1 going out of bounds here. This is going to be out of bounds, but our while loop here is going to catch it, so it's just going to return count as 0. So this is no big deal. After that, we can just return our answer. Let's try running that. Cool. So this question is super similar to the previous one. Again, more of a two-pointer approach, but we're making an adjustment to this count palindromes function. Initially, as we're checking for the longest. Now we're finding the number of palindromes. So every time we found S of L equals to S of R, that means we have a palindrome, even if L and R are the same thing. So whenever we have a palindrome, we increase the count by 1 until we reach the boundary, or S of L doesn't equal S of R. So in either case, we're going to return count and then increment that to our answer. And this is going to look for the odd length palindromes, and this highlighted line is going to look for the even length palindromes. So once we have all the odd lengths and the even length ones, we can just return that as our answer. Cool, so that's this question. Let's move on to the next one. Decode ways. So decode ways, a message, let's expand this here, containing the letters from A to Z can be encoded into numbers using the following mapping. So A is going to be 1, B is going to be 2, there's 26 characters in the alphabet, so Z is going to be 26. So to decode and encode a message, all the digits must be grouped and then mapped back into letters. So what we're given is actually this bunch of numbers in a string, and we want to map it back into letters. And different letters can have different groupings. So for example, AAJF, the grouping is going to be 1, 1, and then J is 10, F is 6, but KJF can have the same grouping. So when we remove all the spaces, it's all going to be 11106. So given a string S containing only digits, return the number of ways to decode it. For example, this 11106 has at least 2 ways to decode it. And the test cases are generated so the answer fits in a 32-bit integer. Okay, so let's look at some examples here. This question is a little bit confusing. So we have S is 12. So there's 2 ways to decode it. We can either think it's AB because A is 1, B is 2, or we can think it's L because L is the 12th character and this 1, 2 is a 12 representing L. So those are 2 ways to decode this 1, 2. So looking at example 2 here, it's 226. So we can say it's BZ, B is 2, Z is 26, so BZ, or it can be VF 22 and 6, or BBF. So the number of different ways to actually separate these characters and change them to be letters. But we also have to make sure that these characters can actually correspond to letters, because first of all here we have 0 and 6. 0, 6 is not anything. 6 is a letter, but 0 isn't. So this can't actually be mapped to anything. We can't have any leading zeros. Okay, so that's this question. Honestly, very confusing, but we can use a DP approach to represent the number of ways we have found at every single index, and then look forward from there. So first of all, we said that we can't have any leading zeros. So if S is 0 equals to 0, we're going to return 0. And this is because this 0 at the start, it cannot map to any letter, and we can't group it with the letter after it either, because 0, 6 is not the same as 6 in this question's case, so we can't map it to anything. So we're going to return 0 if S at 0 is 0. Now let's create our length. Let's let n equal to the length of S, and create our DP array. So DP equals to 0 times n. Initially, we're going to initialize everything to 0, and DP at 0 is going to equal to 1, because we're assuming DP at 0, sorry, S at 0 is not 0, so there's at least one way to represent this character, because this character can be from 1 to 9, and 1 to 9 all match to different letters. So DP at 0 is going to be 1. Okay, so if S, so now what we're going to do is do a for loop. Our for loop is going to start from index 2. I'm going to see why in a second. It's because we have to go back to 2 characters. For example, we have the 26. We're going to look at the number of ways we can do the 2 here, and then increase that by 1, which is this new 26 here. So for I in range, starting from 2 all the way to the length of S, so basically every index, dp at I equals to dp I minus 1, because there's at least I minus 1 ways to do this. So now we're going to look at what we have here. So at index I, we're going to have a character, but we should also consider the character before it, because that could form a new grouping. For example, if we only have 2, that forms one grouping, but if we have 2, 2, then we can split the 2's into 2 different 2's, which is 2 B's, or we can have a 22, which is a V. So we need to look at the value that the current character and the character before this creates, so which is a number. So let's call that value. This is going to be casted into an int from S at I minus 1 all the way to I plus 1. I plus 1 because we want the current index to be inside of it, and this is non-inclusive, so we need to do I plus 1. So if we want the value to be between 10 and 26, because if it's over 26, then this is definitely not going to be a valid mapping. If this is under 10, for example, it's a 9, then the previous character is a 0. And if the previous character is a 0, then this doesn't increase the number of mappings because we have to use that 0 in our current mapping. For example, if we have 0, 9, then we can't isolate the previous 0, so we have to use that together. So if 10 is less than or equal to value, less than or equal to 26, less than or equal to 26, so this is in bounds for a 2-digit number, then dp at I plus equals to dp at I minus 2. So for example, we're looking at the 26 here. We have a new valid way. 26 is between 10 and 26. So we can take a look at how many ways there were to map this to, and then increase that by that amount, because this is again a valid mapping. So another special case is if s of I, this is equal to the character 0. So what happens if s at I is equal to 0? For example, let's create our new test case here. These test cases aren't that great. So let's say we have 20. Okay, this is our test case. So if s at I is equal to 0, then we want the previous character, it has to be a 1 or a 2. Because if it's a 3, for example, it's a 30, then there's 0 ways to map this. We can't use this 0 at all. So we need to make sure s minus 1, s at I minus 1, this has to be inside 1 or 2. So let's say if I minus 1 is not in 1, 2, so the previous character is not a 1 and it's not a 2, then there's 0 ways to map this. So we want to return 0. Otherwise, assuming the previous character is a 1 or it is a 2, then dp at I, we're going to have to use that previous character, because if this is a 0, we have to take the previous character and use it, because this 0 itself can't map to anything. So taking that previous character, dpi equals to dp I minus 2, because this doesn't generate any new mappings. And after that, we can just return dp I minus 1. Sorry, not I minus 1, n minus 1. So looking here, we're starting this for loop starting from index 2, but we haven't set up the index at 1 yet. So we're going to see what the different possibilities are for the character s at 1, and we're going to set up dp at 1. So if s of 1 equals to 0, so it's something 0, for example here, like a 2, 0, what do we want to do? So we need to check if s at I minus 1 or s at 0 is in 1 or 2. So if s at 0 is not in 1 or 2, we're going to return 0 because this doesn't work. Otherwise, dp at 1 is equal to 1, because there's only a single way to represent 20. It's the letter at 20. I don't know which letter that is, but there's no other way to use this 0 otherwise. So let's assume that s at 1 is not equal to 0. So else, we need to check what value this is. So we can look at, for example, this is it's a 12, for example. So if int s at from 0 all the way to 2, if this is less than 27, or let's do less than equal to 26, what does this mean? That means we have a valid number here. We know that this character here is not 0, and the previous character is not 0, so we don't really have to do the 10, but we could, it doesn't really matter. So if that's the case, dp at 1 is equal to 2, because there's two different ways to represent it. The first case is if the previous character and the current character are split, so a and b. The other case is if we use them together. So there's going to be two cases, which means dp at 1 equals to 2. Alternatively, if this is not in range, for example, it's like a 2 and a 9. So 2, 9 is not a valid letter. So the only way to do this is to split the previous character and the current character. So it has to be the letter at 2 and the letter at 9. We can't use a letter at 29. So dp at 1, this has to be equal to 1. So that's all the cases for the first character. Now we've connected this from 0 to 1 all the way to 2 to n. So we can safely return dp n minus 1. So let's try running this. Cool. So even our custom test case passed. Let's try submitting it. So what's the error here? It says string index is out of range at 1 is equal to 0. So if it's possible the string has only length 1, so if it has length 1, then accessing the index 0 is going to be out of bounds. So before we access index 1. So before accessing index 1, we need to make sure the length is not 1. So if n equals to 1, let's just return 1, because if it's a single character, let's create a new test case here. How do I do that? Okay. So if it's a single character like 1, there's only one way to represent it, and we made sure this character is not 0 right at the start. So if it's a single character and it's not a 0, then there's one way to represent it. These characters can be from 1 to 9. Cool. So let's try running that again. Nice, worked this time. So this question, very complicated. I don't really like this question, to be honest. It's very edge casey and not a very good representative early on entry DP question. But regardless, it's a DP question that's on the roadmap, so here we are, we're solving it. And even I messed up this question because I forgot this case and got it wrong, even though I've done this question before. So that's it for this video. This is the first half of our dynamic programming 1D questions. We're going to continue this dynamic programming 1D questions in a future video. So thank you guys so much for watching, and hope you're able to learn something, and I'll see you in the next video.